So if you have any questions, obviously go ahead and don't forget to ask while we're into this, okay? All right, so we're going to be looking at Chapter 9 today. And Chapter 9, as we said, it's titled Further Applications of Stress and Strain. So it really is just building on these principles. So you're going to start utilizing those equations, stress, strain, and modulus of elasticity quite a bit. And then we're going to add another one called thermal stress, thermal strain today. And as we get into that, we'll also get into thermal deformation, thermal stresses. And then we talk about this guy called indeterminate problems. So they're indeterminate because you can't solve them with either statics alone or strength of materials, but the combination of the two, when you can use statics, laws, and equilibrium in conjunction with strength of materials, allows you to solve them. So then they become solvable at that point. There's two primary kinds there, what we'll call a series problem type. So that's when materials, two or more materials, are acting in series. So that's an indeterminate series problem, in other words. And then the other kind is what's called an indeterminate parallel problem, where two materials are acting together, but they're in a parallel form. So we'll explain what that means as we get into that. And you could also do series and parallel problems that are indeterminate, adding the thermal aspect into it, and that makes it really tough. We're not going to do any of that. So we're going to keep it pretty simple as we get into the series and the parallel problems. Okay, so that's the good news. And there's further pieces in this chapter. When you get beyond that stuff, they start talking about some other things like stresses in oblique planes and all of that. So you're really just looking at sections 9.1 through 9.3. So we're not going to do the whole chapter. So just keep that in mind too. Okay. So in chapter 8, we introduced the concepts of stress and strain. So hopefully you have those pretty well down, that you can pretty much define stress just generally as force divided by cross-sectional area, and strain would be deformation divided by original length. Okay, so those are very important. Just hopefully you've memorized those. And then furthermore, we developed relationships between stress and strain where we related that to a material. So that's where you start to bring the material aspect into it. And we developed that concept of modulus of elasticity. So which is the, really remember, that's more of a resistance to being pulled, more or less, or rigidity, you might think of it. And it's a constant for each material, but it also is a constant value or a linear value in a range before it goes plastic. We've related those two together. So what we're going to take a look at now is what happens to stress and strain, or how can we utilize stress and strain to talk about what we call thermal changes, where we increase or decrease a temperature, which vibrates your atoms more or less. And what that does is then that changes the size and shape of a material, which of course will be important to any designer. And then we talk about the indeterminate problems, and those, as we said before, can't be solved just utilizing simple types of equilibrium. So stress, strain, and laws of equilibrium conjunction can be used to solve those type of problems. So we'll kind of see how that works. So let's talk about thermal deformation and stresses first. So you guys all know that as a temperature rises or falls, things are going to change size accordingly. And of course, particularly building materials and structures, this would be a really, really important thing to deal with. You guys have all seen big bridges where you drive across, and usually at one side or the other of that bridge, you're going to see things like, I call them jaws, is where the two things kind of meet together, plates, and those are what you call expansion joints. And those, of course, are in there because that material is going to increase size when it gets hot. And those jaws, those teeth will come together, actually. And if it's going the other way, then they come apart. So you have to have that, allow that thing movement. If you don't allow movement, you're going to get stresses developing on things, and you can actually fail pieces. So I've actually seen on hot summer days, if they don't have enough expansion joints in concrete, that concrete will come together and actually more or less explode. That has happened before. So that's not an unusual thing. So most materials expand with temperature increase and contract with temperature decrease. And we say most materials because water will do the reverse. It actually expands when it gets cold. So there are materials that do a little bit reverse, but most of them that we would consider the building type materials, they're going to expand with a temperature increase and contract with a temperature decrease. And that potential for expansion really has to be accounted for in the design. Okay, and as we said, it's accounted for a couple ways by using that concept of expansion joints. Those can be physical joints that you see, like I said, on a bridge, and then underneath you'll probably have a roller where that thing can roll across with it. And in concrete, they either form those joints in there, or they'll some come back and saw cut. You probably guys have all seen that. And they'll use what's called a slotted bolt hole, where instead of just a drilled hole, it'll be more like a ellipsoid, elliptical kind of thing, where that bolt, can move back and forth, or the bolt stays rigid, but the material can expand in and out through that slot. So those are some examples of what you would see in building design. So that expansion contraction is due to what's called a thermal deformation. So the material is deforming based on that. As we said, it's an atomic kind of thing going on with your atom arrangement and how they vibrate. And so it's changing based on that. And thermal deformation is considered a unit of deformation over that member's total length, or the original length. And then if we talk about it over the total length, then we express that as what we call thermal strain. So remember, strain is related to elongation, or change in length. So it's generalized from your general strain equation, which essentially says that your strain value is equal to your deformation divided by your original length. Okay, and strain, as we know, basically is a unitless number if you do it as an inch per inch. Now remember, some people will call that an inch per foot. That's not a common way of expressing strain, but normally we use it as a unitless number. So the deformation, of course, is what we're really talking about. And that would be typically in inches, millimeters, meters, whatever you're measuring it in. Same thing with the original length. Okay, so this is the generalized equation of strain. But thermal strain is not developed due to axial stress or an axial load. Remember, that would be a load that is parallel with the long axis of the material. But it's due to what we would call delta T. Delta T is what you call a temperature change, okay? And so the greater that change, the more the strains occur. So this is a direct multiplier. That delta T will be a direct multiplier in terms of how much strain is occurring, okay? And the type of material also will play into the amount of strain, because every material has its own constant associated with it when it comes to thermal changes. Just like every material has its own unique modulus of elasticity, it will also have its own unique material constant known as the coefficient of thermal expansion, and that is denoted as alpha. Now do keep in mind, materials are three-dimensional, so they actually do expand or contract in 3 dimensions. We're normally talking about a linear direction, or just a 2-dimensional kind of thing. So sometimes this is called a coefficient of linear expansion. I've heard it referred to as that because it's actually just, we're normally looking at it in one long axial direction. But you can talk about it in a 3-dimensional sense. And then I guess a person that was dealing with a big structure would have to look at it both laterally and axially. And maybe like for machines and those kind of things, they would have to look at that in a 3-dimensional sense. The higher the coefficient of this, alpha, the more sensitive the material is to temperature change. And what that's really saying to you is that for let's say if you have a temperature change of 30 degrees, if you have a higher coefficient, that means that material is going to expand or contract more in that 30 degree than a material that has a smaller alpha value, okay? So steel expands at a pretty good rate, but concrete does not. And it's kind of like we talk about strength of material. When we talk about modulus of elasticity, those slopes of those lines are defined based on that material as well. And they mean something like a higher slope as an object is more rigid, but with a higher alpha, that material is more sensitive to temperature change. So we have a chart, and this is a published type of chart. You can find many different sources. This is out of your book. This is table 9.1, and it can also be found. There's further numbers in Appendix B, and you can see some of these. These are typical material constants, and some of these you might have seen before, because I know I talk about this in my layout class when we talk about steel taping, how that changes your steel tape value. But notice some of the materials, the higher the number here, the more sensitive it is, or the more it will expand. So notice steel's at 6.5 times 10 to the 6th, but aluminum's at 12.7. So these guys, this is going to expand a whole lot quicker or contract a whole lot quicker with the same amount of temperature change. And notice the unit, it's an inch per degree Fahrenheit. So basically it's just per degree Fahrenheit. This just kind of cancels out essentially. Now, it's important to understand it doesn't really matter whether you're inch per inch or foot per foot. It'd be the same number, but it is important that you use the right temperature type. So either Fahrenheit or centigrade. So notice they're quite a bit different. So you got to make sure that you're using the right one. Okay. So that's pretty important, particularly if the problem doesn't give you the number. It just says, hey, you've got a temperature change of so many degrees. You have to go look that up. You make sure that you get the right one. Okay. You'll memorize some of these maybe if you're doing them enough. I use this one out in the field all the time for steel because that's important if you're doing temperature changes for measurement. Concrete's another pretty common one. But you know, the easy lookups, but just make sure you're getting the right one. Centigrade with the centigrade problem and Fahrenheit with a Fahrenheit problem. Okay. So because that thermal strain is dependent on temperature change, we can basically take the strain equation, and instead of defining it as delta over L, we can now look at it as a thermal kind of problem, and it can be expressed as alpha delta T. So alpha, again, is your coefficient of thermal expansion. Remember, its unit is an inch per degree Fahrenheit, and temperature change would be Fahrenheit. So this cancels out, everything cancels out here, and this is left with a unitless number, or you could consider it inch per inch depending on what your unit is. So we normally think of strain as a unitless number. Okay, so just kind of watch that. But so this is the amount of thermal strain that is generated. So again, it's a direct multiplier. These are direct multipliers. As your temperature changes up or down above a standardizing temperature, you're going to increase more strain or decrease it going one way or the other. Okay. So basically what we're saying is we can now solve this into deformation, because we also know, you should recognize, by taking the strain equation, we can rewrite it and solve for deformation. Okay. So we normally think that strain is equal to deformation divided by L. So we can solve for deformation and say deformation or change in length is equal to your strain times L. And by substituting the previous equation into this, we get this thing called thermal strain. Okay, so taking the thermal equation for strain, which was alpha delta T, we plug that in, we get thermal deformation is equal to alpha delta TL. This is going to be a pretty common equation right here that you'll use. Okay, so the delta thermal is your deformation caused by a temperature change. Okay, so let's take a look at a couple of problems. There's a couple of problems out of your book, and like I said, you've probably seen these guys before, but we'll go through a couple real quick. This stuff's pretty straightforward, I think you'll find out. So let's take a look at, let me switch over here, and we'll shoot over to my taskbar and grab my whiteboard here. So in this problem, they give you a surveyor's tape that's 100 feet long, and they give you a standardizing temperature. So they tell you that the original L in this thing is 100 feet. And the standardizing temperature, which I call final initial, is 68 degrees Fahrenheit. Now, what that's saying is that when that steel tape is manufactured and calibrated to be 100 feet, it was done under a temperature of 68 degrees. So if you're above or below that temperature, the readings on that tape are going to change. That's what that's telling you. Okay. So they tell you further that you're going to take a measurement on a summer day when the temperature is, I guess I should, instead of let's calling that, I was meant Fahrenheit. Let me do something here real quick. Instead of calling that temperature or Fahrenheit or TF, let's call that T initial. Sorry about that. I was thinking Fahrenheit. So my initial temperature is 68 degrees, and my final temperature at time of measure is going to be 95 degrees Fahrenheit. So as everybody would understand, because of that temperature change, that steel has expanded. So it's not reading 100 feet exactly from 0 to 100. It's actually should be a little longer. So what we're going to see is what's the actual length of the tape. So we want to know what that final length is. And since it's steel, it's a steel tape, we know that alpha, if you look that up, is 0.1234565. And that would be in inches per inch per degree Fahrenheit. Okay. So basically, to determine your thermal change, it's just going to be thermal change is equal to alpha delta T times the original length. So alpha 0.00000. Oops, I think I got one too many. It's 5 zeros. 1, 2, 3, 4, 5. 65 times delta T. Delta T is your final minus your initial. And then we have L, which is 100 feet. So since that's the unit, basically everything else cancels. So when we resolve that, let's run those numbers and see what we come up with. So when I generate that, I get a number. So I get that number right there. And notice that's in feet. So that's about 2/100ths of a foot. So it's not much. We had a 27 degree raise in temperature. So our delta T was actually 27 degree rise here. So in 27 degrees, we've raised almost 2/100ths of a foot, which if you're looking at inches, that's still not very big. So that would be basically 21/100ths of an inch. It's not a huge number, but it's enough that if you were having to deal with something, it could be an issue. Does everybody see how that works? Pretty straightforward process. That equation shouldn't be something you haven't seen before. Like I said, if you did the basic level surveying course or the other surveying course, the construction layout course, we talk about that. Okay. Any questions on that one?
Where did you get the 0.5065 from?
That is the material constant for steel. Okay.
Okay.
So the statement of the problem, if you look on page 280, he tells you that it's a surveyor's steel tape. Okay. So if you go back to that chart, I don't think it tells you in the problem. Okay, he even says in the problem that steel has an alpha of that number. He puts it, he rates that actually is. It's probably easier to key in your calculator like this. That's the same number, okay. So, but it's given to you either in the statement of the problem as the material, which means you have to go look this number up, or it'll be given to you in the problem, okay? Does that make sense
Okay.
now?
Yep.
So in this case, he just told you it was a steel tape, and then it said, okay, you have to go look that up, okay?
Yep. Seems pretty simple.
It's pretty simple. All right, so let's take a look at another example. We're gonna see. I think you're gonna find these. Now they can get a little involved. Okay, just understand it's like anything else. But I think you'll see that they're not too big of a deal. So let's take a look at the problem too. It tells you that a concrete slab that is 60 feet long is calculated. They want you to calculate the temperature rise needed to have a deformation of 0.25 inches, a quarter of an inch. So what they're telling is you're going to have, this is concrete, okay? So you have concrete, and they're going to give you the deformation. So he tells you that the deformation is 0.25 of an inch, and that's a thermal deformation. What they really want to know is if an original length is 60 feet, okay, what would be the delta T that would be required to give you that deformation, okay? So for instance, if you have an expansion joint of a quarter of an inch, that's what that's saying essentially is what temperature rise would it say to make that thing close essentially? And since it's concrete, we have to go look up the material constant for concrete, the alpha for concrete. So if you go back and look on the book chart, it shows you for concrete 5.5 times 10 to the 6th. It's actually easier to express it like this. And again, remember, make sure that you are in the right units. So this is the inch per degree Fahrenheit one, okay? So that's all important. So if we look at the equation, it basically says that the thermal strain, or the thermal deformation rather, is equal to alpha delta TL. Well, basically what we're solving for is delta T here. So therefore delta T is going to be deformation divided by alpha L. Okay? So if we just plug those numbers in, just make sure we're in the proper unit. That's in inches. Alpha is 5.5 times 10 to the, that should be -6, by the way. -6, sorry about that. Times L, what is the unit of L in this problem right here? It's what? Feet initially. So we want to get this into what down here?
Inches.
Yeah, be careful with that. So I'm just going to call that 60 times 12. Is everybody okay with that?
Yep.
All right. So inch per inch cancels. The inches per inch cancel in this, and the Fahrenheit flips up to the top. So you're going to be in a delta T of Fahrenheit. So that all makes sense from a unit standpoint. So let's see what we come up with. And it shouldn't be a huge number. I wouldn't expect it. If you're getting like a really, really large number, you probably got a mistake. But I came up with 63.1 essentially. That would be degrees Fahrenheit. So what this is saying is at whatever standard temperature you're talking about, we don't know what the actual starting temperature on this problem was, but whatever that starting temperature was, if it rises up 63.1 degrees Fahrenheit above that, basically that would cause that deformation of that. Okay. Any questions on that? If this temperature increased, what that says is this would be 60 inches plus 0.25, okay, or 60 feet plus 0.25. So it would elongate by that amount. If this was going the other way, if that was below the standardizing temperature, it would be 60 feet minus that. So it would have decreased. So sometimes they're going to ask you that kind of thing too. You'll see some of these problems where we'll get into that. Does everybody understand that?
Yeah, but I got 67.75.
Did you? Yeah. Let's see.
I don't know, maybe I did it wrong, but I did it twice.
I didn't get close to either of those numbers.
You didn't?
No.
Okay.
I messed up.
Well, here's how I do this. I mean, you guys can do it differently. Are you keen? 6 point, that's 5.5, right? Times 10 to the negative 6. Okay, so 5.5 times 10 to the negative 6 times 60 times 12. I get like a pretty small number. It's 0.004. And when I usually use a 1 over x. So then I multiply that 1 over x times 0.25. Yeah, I'm coming up with 63.1.
That's what I got too.
Okay.
So I rounded the 0.04. I got 0.00369. So
okay. Be careful doing that too early. If I were you guys, I'd try to let your calculator do most of your work. Okay. Don't write stuff down intermediate steps, or if you do, carry it out a little bit further, because it does. The ultimate answer rounds a little bit. But if you came up with 63, 67, I mean, you know, that's not that big of a deal, but that probably isn't the better number. Okay. 63 is the better number.
Okay.
All right.
Yep.
Any questions?
Nope.
All right. So that's dealing with thermal, what we would call thermal deformation. So let's go back and take a look. Let's build on this concept a little bit now. Okay. So we basically looked at problems 9.1 and 9.2, and you're going to have some more to deal with. So essentially, this thermal equation here, thermal deformation is alpha delta TL. Very, very common equation. So you're going to see that a lot. You see it in physics. You'll see it in other things as well. So remember, it's important when you do this, make sure that your units work, okay? Alpha is essentially unitless, although it does carry the temperature component with it. So make sure you get the right alpha value. And same with delta T, you're in either Fahrenheit or centigrade. And L, usually make sure you're working in the proper unit also. It's typically, if you're in imperial, you probably want to be L in inches. If you're metric, you probably want to have L in millimeters. Okay, so just kind of watch those. Those are your big pitfalls. Okay. All right, so we can look at it differently now. So let's say a member is not allowed to move freely under temperature change. And if that's the case, then you're going to get a stress that's going to develop. So this thing, in other words, is going to want to expand or contract, but you're not letting it. So for instance, you might have a bar between two immovable or fixed walls. And if that thing heats up, that bar heats up, it's going to want to expand into the two walls, but the walls are going to push back and they're not going to let it. So what this will do is tend to develop a thermal stress or a stress associated with that. So that amount of thermal strain is there. It wants to expand. That's your thermal strain, or that wants to deform. But something is causing that to not happen, and that generates that axial stress. So the stress developed in a member restrained from thermal deformation can be defined by relating your general equations for stress and strain and thermal. So in other words, we know that modulus of elasticity is stress divided by strain. So you can rewrite that so that stress is equal to E times strain. And we also know that thermal strain now is alpha delta T. So essentially we can substitute one into the other. So by substituting the thermal strain equation in for that, we get thermal stress. So notice that thermal stress now can be related as alpha delta TE. So this is pretty cool because now we're taking all those material constants and we're starting to interrelate them. So this is actually now really truly talking about materials. Anytime you're using E, you're really talking about material specific. And the same thing with alpha, which we developed in chapter 8. So notice thermal stress is going to carry the same units that normal stress would be. It's going to be pounds per square inch or kips per square inch. Or if it was a Newton or if it was a metric problem, what unit would stress have? Anybody tell me? Nobody knows the metric equivalent for stress units?
The KMS.
KMS, which K means what? Well, I don't agree. Okay.
No, I guess
No,
it's not.
it's either going to be the unit that you'd normally force would normally be newtons, and your area would be like meters squared, so newtons per meter squared. Or another way of expressing a newton per meter squared is a Pascal. Okay, so just like normally in imperial, we talk about pounds per square inch, kips per square inch. If you're imperial, that's fine. But if you're metric, just remember you're either in probably pascals, could be kilopascals, whatever, or you're going to be a newton per meter squared. So alpha is your coefficient of thermal expansion, delta T is your change in temperature, either in Fahrenheit or centigrade, and then E is your modulus of elasticity. What units does the modulus of elasticity carry? Anybody remember? Carries the same units as stress. So modulus is in PSI, KSI, or it could be in pascals or kilonewtons per meter squared. Okay. So we can look at a problem if you want to take a look at. Let me see if I got a good problem here in a minute. We got a bunch of stuff here. So we're going to see how the stress develops when we expand or contract something. So let's take a look at problem 3 out of your book. Let me grab this whiteboard here again. So I'm going to clean this up. So in problem 3, they give you they show you a steel bar that is fixed between two immovable walls. So basically, let me go ahead and draw this picture real quick. Yeah, let's see, I'll do this. So I got a wall here that's fixed, and I got a wall over here that's fixed. And I've got a steel bar that I've attached rigidly between them. So we've got a steel bar, runs from here. So that's my steel bar. So we have a distance that's given between the wall. So they tell us that this is 20 inches in originally. So the thing to understand here is that this is not going to change. Okay. So that's not going to change, that 20. They tell us that it's steel. So we're going to need the material constant for steel in terms of alpha and E. So let's see in the book. Let's see. If we look at steel from the table, it gives us 29. Going back to table 8.1, I'm going to go back to 8.1. See what we come up with for steel. You guys let me know if you find for steel. Oh, come on. Having a hard time finding my 8-1 table. There it is. It's on page 256. They give us for steel 29 times 10 to the 6 psi. I think I mentioned that steel will have varying ranges of modulus. It depends on the amount of carbon in it. So you can go anywhere from 28 times 10 to the 6th up to 30 times 10 to the 6th. So a lot of times the problem, if it's material specific, they'll give you that information. So we also know the material constant alpha, and that's 6.5 times 10 to the negative 6th. And again, that's your inch per degree Fahrenheit. So what they tell us is that the existing temperature is 50 degrees. So your temperature initial is 50 degrees Fahrenheit. And they're going to let this go up to a final temperature of 100 degrees Fahrenheit. Okay. So they want to know what stress will be created in this bar when the temperature increases. Okay. So we can solve that pretty directly. Thermal stress, this is pretty simple. We actually don't even know the cross-sectional area of this bar. So you might think if I'm dealing with a stress problem, I would need the cross-sectional area, but I don't, because I have this equation that we just looked at that says your thermal stress is equal to alpha delta T E. So we have everything we need. So delta T, remember, is going to be final minus initial, which gives me 50 degree change. And alpha, so we just plug it in. Times 50 times modulus of elasticity. Let's see what we come up with. I get 9,425. What are you guys coming up with?
9,425.
Okay, what's the unit on that? We're talking about stress, right? What's the unit?
What would it be? Would it be inches?
No, stress is either in PSI, KSI, or kilopascal per or Pascal. So let's look at the unit here. What's the unit of alpha? It's basically degrees Fahrenheit, right? Because the units cancel. And this is actually, this would be 1 over Fahrenheit if you were looking at the unit here. This is actually in Fahrenheit, so these cancel. And this guy brings in PSI, so this would be what? PSI. Okay, does everybody see that? It's pretty important when you look at units, but just think about the unit that stress has to be in, okay? That's pretty important. Okay, do you see how easy this equation was?
Yeah, this isn't bad.
Okay, let's look at this a different way though. They gave us L, right? We didn't even use that, did we? But we could use that because we could calculate that stress first. So let's take a look. I'm going to redo this. Let me erase this equation. Has everybody got this down?
Yeah.
By the way, you could also move this decimal place over, and you could express that as 9.43 KSI. Okay, these would be the same number essentially. Okay, so let's Let's go ahead and I'm going to erase this down here. And let's look at let's calculate it based on a strain relationship, because we can do that too. And see where that, because you notice that they give you the length and it's kind of like, well, what did I do with it? Well, we didn't have to do anything with it. But we also know that we could solve a amount of deformation, a thermal deformation. Thermal deformation is equal to alpha delta TL. So alpha again is my 6.5 10 to the 6th times 50 times L, which is 20 inches. Okay, let's see what we come up with here. I get 0.0065. Let me redo that with 5. What is that number? First of all, what's its unit? What is its unit?
Would that be inches?
It would be inches, correct? Because this is canceling, the two things are canceling out here, so the only thing that's left is inches, so this is inches. Okay, so good. Now that it's inches, what does that number mean? What is that? What's that telling me? Anybody know what that's saying to you? That's saying that because this temperature has increased, this bar wants to do what? It wants to expand that amount, but the wall's not letting it, okay? It wants to expand by 0.0065 inches due to that temperature change, but because that wall is immovable, it won't let us. So what we can do is now solve the stress that's developing due to this change. We know that stress, remember, we know that modulus is equal to stress over strain, right? And we can write stress as force divided by cross-sectional area. Actually, we don't even need that, do we? We just want to solve stress, so let's do this. Let's solve for stress. Strain can be defined as deflection over L, correct? Which another way of writing that is so if we solve for the stress here, we can see that the stress would be deflection times E divided by L. Okay, so going back to the initial definition of modulus of elasticity, stress over strain, I want to solve for stress due to that amount that thing is increased or wants to increase, and it won't let it, the wall won't let it. So what we have is deformation. We ultimately can get deformation times modulus of elasticity divided by original length. So that gives me 0.0065 times E, which is 29 times 10 to the 6th PSI divided by 20 inches. Let's see what we come up with. Isn't that interesting? We should get the same number, or we get the same number, and we should get the same number. If we don't get the same number, something's wrong. So this was a two-step process, essentially, if we were doing it the other way. where the first equation was more streamlined. It took us right there really quickly. But just by being able to manipulate stuff, you can get there where you need to be. Any questions on that? Is everybody following me?
So would that happen every time? Would you get the same answers for this type of problem? Would you
You
get the same
better,
answers?
right? You better, because if you're not getting the same answer, you got a problem. Okay.
Okay.
Because what's happening is, remember, this was a fixed condition, okay, initially. So this 20 can't change, right? So with that temperature change, that's what it wants to be. That bar wants to be 20 inches plus 0.0065. The walls aren't letting it, okay? So yeah, those equations are exactly the same. They're just written differently, that's all, okay? The other cool thing is we didn't even need to know the area here, okay? You're going to start to see also, we're going to now be able to figure out things like the amount of force that developed and that kind of stuff. That's where we get into some of this. Because if I did give you the cross-sectional area, you could tell me the amount of force that developed due to that. So we'll take a look at that here in a bit, okay? But we're going to get into some of these other problems. So everybody okay with this stuff? It's not too bad. This is just got to think about it. Think about what it means, though. Think about what this number is telling you, okay? That's important. Think about units. That's really, really important. As I've kind of said initially about strength materials, it's much more of a unit issue than it is in statics. Because, you know, in statics, we're just really dealing with a force and a direction. That's all. But here we're dealing with other things as well. Okay? Ready to move on?
Yeah.
Okay, you're going to have some problems to do on this stuff too, and we'll go over this more on Thursday. So just like I said, I think it's pretty straightforward, but the indeterminants now, they're going to get a little bit different. So let me, I'm going to clean this. Well, we'll come back to it. All right. So let's go on a little bit now. Let's take a look at indeterminate problems. So as long as you're dealing with a single material, that's really everything we talked about. Single material, it's not a problem, but structures are typically composed of members of usually more than one material. And when we have that going on, then we've got what's called a composite member. So composite members are going to bring different problems to the table, because what's going to happen is now you have two materials, so that means they have two different E's. They have two different modulus of elasticity values. They're also going to have two different alpha values. So that's going to create problems, especially when you talk about stresses and forces. These are going to have to be found in such a way that it's adequate for both members, or both materials, I should say, in the same member. So that becomes a different problem. And these two problems are not solvable using statics and equilibrium alone, because the force that develops in each material is going to be different, depending on what's going on there. So because of the different materials within that member, different E's, different alphas, those forces are going to develop differently. So these problems become indeterminate because you can't just solve them using statics alone. But when you combine the laws of statics and equilibrium with the laws of strength of materials, then they become solvable at that point. So we're going to take a look at some of these. So there are two types of indeterminate problems that we can see and we'll investigate. And one is where we have a member with two individual pieces arranged in a series. Now, we're not going to talk about multiple different types of materials. So we're typically going to be talking about two. For instance, concrete and steel bonded together. Or you might have brass and aluminum bonded together. So usually two materials. So we can either arrange these guys in what we call a series configuration, or we can arrange them in what we call parallel. Now, figures in your book, if you're referring to these, I want to show you some of these. On figure 9.3 shows you a pretty good example of what we would call a series problem. Let me just flip over. I'll just draw a real quick picture right away so you can see this too. So in a series problem, or a series type material, what you would have is you might have a bar of some type of material like that, rigidly bonded to another bar of another type of material like that. And so what we're saying here, they're in series, okay, one stacked against that like that. So this might be material A, and this would be material B. So that's what we're saying. So then when we apply a load on this P, the loads are going to be different, well, depending on what you're doing here, but they experience loads differently because you have a modulus of elasticity for A, which will not be equal to the modulus of elasticity of B. So those will not be equal. And your alpha values, if you're dealing with temperature of those two materials, won't be equal. So because of that, you're going to have other problems that develop, okay? And this is independent of cross-sectional area. You could have the same cross-sectional area and you can have the same length, but it really has to do with the materials themselves specifically. So this is what we call a series problem. So the other type that develops is what's called a parallel problem. And a parallel problem means these guys work together in the same axis. Let me show you. So for instance, your classic example of this type is, let's say you have a concrete column, and inside of this column you've got steel reinforcing rods. So I've got a steel reinforcing rod there, and maybe a steel reinforcing rod here, and maybe a steel reinforcing rod here. Okay, so we have concrete, whoops. We have concrete on the outside. So that's concrete. And then you have steel here, here, and here. So those two materials, notice they're parallel. So they respond differently because, again, you have an E of steel and you have an E of concrete, and they're not the same numbers, okay? Interestingly enough, though, what we normally do in these problems is that we'll say that the L value in this type of problem, they're going to be the same. So the L for steel and the L, the length, will be the same. So these are going to cancel out in these problems. That's going to be one thing that'll be different. So we're going to look at ways of solving the parallel and the series. We're going to take a look at series first. So let's go back here. Okay, so let's look at series type problems first. So a member in series, remember, is composed end-to-end fashion, okay? And typical problems involve two materials fixed between, like, say, two immovable walls with each piece acted on by a different force. So figure 9.3 is showing you that, okay? And when we just kind of looked at, and we'll draw that up here, but we have an applied load P in that thing that's going to want to cause reactions within the wall, PA and PB. And by using equation of equilibrium, so we're using statics here, we can say sum of forces in an x direction. We're going to have the force in A minus the force in B plus the force. So let me flip over to this diagram here. So I drew this up. So here's we've got our two immovable walls, the left wall and the right wall, and we have two materials. This is material A, this is material B. And we are generating a force of reaction, force of material B and force of material A, because we're doing an applied load right here. So this load is pushing this way or pulling that way. So this will react back this way. And since this is pulling on material A, it's going to react this way. So if we go back to that equation, notice I have minus PA minus PB plus PB, or plus P rather, has to equal 0. So what we're looking at, this is statics. But this equation is unsolvable as it stands, because even if we know the value of P, we don't know the value of PA and PB, because we can't just assume that they're half, okay? So this becomes unsolvable, just straight statics. But we can then start looking at the strength of materials. So that equation alone is unsolvable. But we do notice that the amount of material A stretched has to be offset by material B. So in other words, what we're saying is the amount of deformation between those two has to be the same, okay? And again, if we're looking at that, if the material is, I think I got that reversed, stretching, I would probably say positive and shortening negative. I just put that's arbitrary. I would probably do that differently, okay? But if we go back to that diagram again, here's what we're saying. Because this force, because we have this force P on here, it wants to pull this material. So this material is going to elongate, and this material has to compensate by decreasing because the distance between here is fixed. Okay. So again, back in this, I would probably do this differently. Stretching is positive, shortening is negative. So essentially what we're saying, the amount of deformation of A and B has to equal 0. So therefore they have to be the same number. So when we look at that, we can remember that deformation is related as PL over AE, okay? So if we substitute deformation of A and deformation of B, what we have is PL over AE for A and PL over AE for B. What we can then do is, just by doing some rearranging, we could put this side over here, we can pull this over here, and we wind up with dividing one equation by the other. Notice what we've got is the force of A is going to be equal to the force of B times L over AE for material B times AE over L for material A. So we're going to know L's, we're going to know areas, we're going to know E's. We're going to get a number here in terms of PB, which we can then plug back into the initial equation, and we'll be able to solve this thing. So we're going to take a look at a couple of different examples on this. I got some good ones on here, so let me give you a couple of examples here. Okay, so let's this may seem a little confusing at first, but you'll see it's not as you get into it. Just like everything else that you get into in this stuff, it's not too bad. But everything relates back to stress, strain, and all that. Now, you can also put the temperature component in this, and we are not going to do temperature components on this, okay? So, in general, what we're going to do is take a look at a problem, a couple of problems actually I want to do. And I want to do a couple of series problems with you, okay? So at least maybe 2. But we're not gonna, your book talks about a thermal addition. So besides a force, you can also have a thermal addition in this, and we're not gonna deal with that, okay? So I'm gonna give you a picture. Let's draw a picture up here. Let me draw one. So we're gonna have an immovable wall here. Okay, so that represents an immovable wall. We're going to have basically about right in the middle. And let's put it just over here. I'm going to have a bar that I've attached rigidly. So we got a bar here. And we have another bar. So these bars are going to be in series. Okay. So we're going to have 50 millimeters. Now this is a metric problem, so they get messy. So the length of that bar is 50 millimeters. The length of this bar is 40 millimeters. Okay. This guy is steel. This guy is aluminum. And we're going to put a force here acting that way of 20 kilonewtons. Okay, so we have to know a couple other things. For the steel, we know that the area that's just going to be given to us is 800 millimeters squared. And that your E is 200,000 megapascals. For the aluminum, we're going to have an area, a smaller area, 400 millimeters squared. And you're going to be an E value of 70,000 megapascals. Okay, so there's our values. So here's what we have to look at. Okay, on this problem, we want to determine the amount of force in the reaction of the aluminum and the amount of force in the reaction of the steel. So what we have going on here, if we look at this, if this guy's pulling this way, this has to react this way. So we're going to have a force in steel, we'll just call that P sub S. And since this is pulling the aluminum, that aluminum is going to react that way. And so we're going to call that force of aluminum. So from a static standpoint, we would say that sum of forces in X have to equal 0. So we would have P of steel plus P of aluminum minus 20 kilonewtons has to equal 0. And so all that really tells me is that the force of the steel plus the force in the aluminum is 20 kilonewtons. Everybody follow me so far?
Yeah.
Okay, so here's the other premise that you pretty typically work with on this type of problem. Is because the wall is fixed, okay? The wall's fixed at 90 millimeters, it can't move. So that means the deformation of the steel is going to shrink and the deformation of aluminum is going to increase. So what that says is because it's immovable, the deformation of the steel, we'll call that a negative, plus the deformation of the aluminum, that's increasing, has to equal 0. So in other words, what we're saying is the deformation of the steel has to equal the deformation of the aluminum. Everybody agree with that? Because it's an immovable wall. Now, if you have a situation where it's not immovable, like you might, if you just have two materials sitting on top of each other and you just put a force down on them, that's not going to be true. They'll deflect, okay? Okay, everybody okay with that? So taking this equation, we know that deformation in general is just equal to PL over AE. All right, we can derive that. Does anybody need me to derive it? Or are we okay with that? You're going to go with that. Where did I derive this from? Going back to the modulus of elasticity is stress over strain. So taking this, you can rewrite it in this form. Okay? Is everybody okay with that? That's important.
Yeah.
Okay. So I'm going to erase that because I need the room. I might have to erase some of this other stuff. Okay, so what I'm going to do, I'm going to take and plug that PL over AE into each one of these. So what I have now is, for the steel, I have PL over AE for the steel has to be equal to PL over AE for the aluminum. So all we're saying is the deflections have to be equal, and then I plugged in the values for what that actually could be defined as. Everybody see that? And what we're now going to do is solve for either PS or PA. So I'm going to solve for PS. What I can do is solve that. I can pull that PS out of there, and I get L over AE for steel. And I'm going to pull the PA out, and that's going to be L over AE for aluminum. When I take and divide this equation by L over AE, I have to divide that equation by L over AE. So this just basically comes over here. What happens is this then goes to PS is going to be equal to P of the aluminum times L over AE for the aluminum times AE over L for the steel. So I just brought this guy over and it flops like that. All right. So now we can plug all of the information in that we need, and we can solve for one in terms of the other and plug it back in here, and we'll see what we get. So let me solve for the steel. Force of the steel is going to be equal to the force of the aluminum. Now you're going to have to watch your units on this one. The length of the aluminum is what, 40 millimeters? So we want to convert that to meters. So 40 divided by 1,000 equals 0.04. So we're going to have 0.04 divided by the area of the aluminum is 400 millimeters. So we need to divide that by 1,000 squared, remember? So that gives me a very small number. Yeah, I'm going to clean this up a minute. Sorry about that. I'm going to run out of room if I don't. I'll bring that guy back here in a minute. So I have 0.0004, and then we've got the aluminum has what, 70 megapascals. So I'm going to multiply that by 70 megapascal or 70,000 megapascals. So this guy right here then gets multiplied by A over E. So A of this 800 divided by 1,000 squared, because again I'm converting the millimeter area into a meter area. That goes to 0.0008 times the amount of modulus of elasticity, which is 200,000 megapascals. And all of that is divided by the original length, which is 50, so that's 0.05. So all this mess is going to yield me, let's calculate this number and see what we come up with. So it's going to be a ratio, essentially, of what's going on there. Be careful when you do the math. Let's see what we come up with. Well, I already made a mistake. Got a number. I'm going to put my number down and you guys can let me know if you got that. I get 4.5714, and that would be P of the aluminum. So what that's telling me is that the force of the steel is 4.5 times the force in the aluminum. That's what that's giving me. Did anybody get this number right here? Is everybody working on that right now?
Yeah, I'm still trying to figure out how to get that.
Okay.
I'm
Let me
working
know.
on it as well.
Okay. Well, piecemeal, what I normally do is I'll just do this side first and multiply by that. Whatever you do, just take your time with it. In general, it's either going to be a number less than 1, depending on whether you saw steel or aluminum, and this number is never going to be very large either. I mean, it's not going to be like 500 times or something. That would really indicate something, probably of a mistake. Now, if you had a huge difference between your modulus of elasticities, that could make a big difference, or your areas, but in general, it's not going to be that big of a number.
Yeah, I got that.
You got that?
Yeah.
Okay, so now that we understand what that is, what we can do is we're going to plug this guy back into our statics equation. Okay, so I'm going to clean this up a minute and show you what we're going to do now to solve this. I'm going to get rid of this equation, okay? I can probably get rid of this equation too. All right, so now that we know that, I'm going to take this equation and write it up over here. So we know that P of the steel plus P of the aluminum has to equal 20 kilonewtons, right? That's coming from our statics. And we know that P of the steel is 4.571 PA. So I can plug this guy into here and I get 4.5714 PA plus PA has to be equal to 20. When I add these two together, don't forget you have a coefficient of 1 out here. So what you get is PA is going to be equal to 20 divided by 5.5714, and that'll tell you the amount of force in the steel, or the aluminum. So you get 4.38 kilonewtons. Is that what you guys got? Let me check that. I'm not sure I got that right. I might not have added the 1 in there.
I got,
Something different.
yeah, I got 3 point.
Yeah, I think you're right. I think I blew it. Let me check mine. I think I forgot to add the 1, even though I said I did. Yeah, that's wrong. That's my bad. Sorry. So this should be 3. What'd you get? 3.58?
5, yeah.
59? 59?
Yeah, 5.9, yeah.
Okay. So that tells me that we have 3.59 of kilonewtons of the aluminum. And so the steel is just going to be equal to 20 minus the force in the aluminum. And that gives us that the steel is taking more of that force, which should kind of make sense. And that would be 16.41 kilonewtons. Okay? You guys get that? There's one answer. There's another answer. So further, what you could answer now is if you were asked, what would be the stress in the steel and what would be the stress in the aluminum? Could you answer that question now? If we wanted to know the stress in the steel, the stress of the steel and the stress of the aluminum, is that something we could answer? What's the definition of stress? Nobody knows the definition of stress? Definition of stress is what? Force divided by cross-sectional area. Do you have enough information to solve this? We know the force in the steel, right? We know the force or the cross-sectional area of the steel. That was given. We could solve that. Let's go ahead and we'll do that. I'm going to get rid of this. We don't need this anymore. So if we wanted to solve the stress in the steel, it's going to be the force of the steel divided by its cross-sectional area. So the force in the steel we said was 16.4 kilonewtons, and the steel has an area of 0.0008. So we get 20,513. That would be kilonewtons per meter squared, so that would be a kilopascal. And the stress of the aluminum is the force in the aluminum divided by its cross-sectional area. That's 3.59 divided by his area of 0.0004. We get 8,975 kilopascals. So this problem, doing it from a standpoint where you're applying the statics and you're applying the strength of materials, you can solve a lot of different stuff. Is everybody following this a bit? Anybody struggling with anything that I did there?
Not really. I know you're just plugging it back in. It's just a lot.
It's a lot, and you're going to have to just do some of the problems, but they're going to come down to be the same type of thing. Okay.
Yeah.
Now, here's the one thing. You could put a real wrinkle in this, and we're not going to, but some of the problems, if you read this chapter, he'll talk about thermal deformation being added into this. That brings a whole nother can of worms to it, because in the equation, what we were dealing with down here, now you'll have a thermal component. Okay, we're not going to deal with that. Okay, just so you guys know, we're not going to deal with that. All right, so we are going to keep that a little simplistic, just from that standpoint. Okay, but you pretty much go from the premise, as if it's an immovable wall, that the deformation of these two guys has to be the same. Okay, and then you can relate it back to that equation that we just said. All right, you ready to move on for one more thing here? Take a look at parallel problems.
Yeah.
Yeah.
Okay. We're gonna work on this on Thursday too. So if you're not catching this, we'll have plenty of time to work through that. So what I want to do is focus in on chapter 8 material, or finish chapter 8. See if there's any questions relevant to that, and then we'll work on problems for chapter 9. Okay. So that's kind of what we'll focus on. So we'll have plenty of time to work these problems. And I'll have your test back too, by the way. They're looking a lot better than the other one, by the way. So That's all good news. Hopefully I'll have your test grades posted by tomorrow. Just need to, I might even do it today if I get time. Okay, so any questions then?
No.
Okay, well, we'll move on then. We're going to do one more application. So realistically, guys, I wouldn't say just memorize this equation, but this is pretty much what you're always going to be looking at here, okay? And it goes back, you got to look at the statics. You know, in this picture, you're going to always have a statics. I should have probably had that as a lowercase a and b here. I got a few things I need to clean up on my slides. The other thing is typically, stretching would typically be considered positive and negative. So, you know, that's just that, but it is arbitrary. So it really doesn't matter whether I call it positive or negative, just so that I make them different. But what this is saying here, which is important premise, is that the amount of deformation in the one material has to be taken up by the amount of deformation in the other. So in other words, the deformations are going to be the same. And then utilizing that concept, you bring this guy over here, becomes positive, and plugging this guy in for each material, you come up with this equation. You should be able to derive this if you need to, okay, or any component of it. But again, don't just necessarily memorize that, but that's what you're utilizing a lot, okay? So we're gonna now take a look at parallel problems, okay? And they're pretty similar. There is a couple things that are a little bit different that we'll see here. So when we have members of different materials ranged in parallel, it's going to be similarly indeterminate, but it's going to be a little bit of a difference how you look at it. But here's some examples. You guys have all seen concrete columns with steel reinforcing in them. That's pretty typical. So that's a good example where you have, you know, steel reinforcing running parallel to a column. So these problems are going to involve two members, either in compression or it might be in tension. Okay, so you're either going to be dealing with compression or tension. That figure 9.5 that he shows you in the book is pretty standard for what we would be looking at for this type of problem. I created a little picture for you as well. But you have an applied load P that's going to cause reactions in each material, and that should be PA and PB, P sub A, P sub B. So again, I need to clean these up a little bit. But this is a little different because in this case, notice that these are maybe the same direction. So some of those other ones might be going in different directions. But in this case, let's see, I should have a picture. Okay, here's my picture. Where that's coming from, the statics is coming from. If I define this material as PA and this material as PB, these two guys are both going up and this is going down. So when I look back at the equation here, I've got both of them acting up and that one acting down, okay? So that's similar to what we just had, but we're using statics here, but of course it's indeterminate, okay? And again, equilibrium alone is not gonna make this solvable, but by dealing with the material specific information, we can solve this. And particularly it's important with parallel materials because if they deform unequally, you're going to have one material ripping the other apart, so you have failure. So one thing that's always true, we always look at these, is that the deformation in each material has to be equal, okay? So the material in A and the material in B, and in other words, if they're being pushed down, they're going to deform the same amount. If one doesn't do that, then the one's going to try to rip the other one apart, okay? So the steel, in other words, has to deform the same amount the concrete does, and vice versa. If you're looking at that concrete column loaded, and that's a steel reinforcing. So that's one premise that's always going to be true in these parallel. The other thing we're going to look at is that we'll see is that the L values are typically going to be, we're going to call them the same. So notice in this equation, when I plug those deformations in for A and B, I have L on this side and L on this side, or if I bring it over, however I want to look at it, those L's will cancel out. So notice what happens here in this, we don't have the L value, it's just related by, it's just a ratio of the area times the modulus of elasticity for the one material divided by the area times the modulus of elasticity of the other material. So this ratio then defines the amount of force in this one and the amount of force in that one. So that's one of the only big difference here is the case that the L's are going to cancel out on you, okay? So we're going to take a look, we'll take a look at a couple of examples here. I'm going to look at problem 9.6 out of the book with you, and I have a couple other ones, but we'll just see how we do on that one, and if you guys want to look at some other ones, we'll take a look at it, okay? So I think, yeah, that's it. Let me go ahead, and again, you could also have thermal issues developed in here, and we're going to skip that whole thermal issue, so don't worry about that. So let me, I'm going to go draw a picture, and then we're going to define everything, okay? So we have a concrete column that we're going to load, and this concrete column has rebars in it. So I'm going to put this concrete column like right here, and I've got rebars in it. On the side, you're going to look at, you're going to have two rebars that you're going to see on the side here. Now from a top view, if we're looking at this in the top view, what we would have is 4 circles. I'm not going to be able to do circles very well, but let's see, we got 1 rebar here, and 1 rebar here, and 1 rebar here, and 1 rebar here. And of course, they would typically be in a nice pattern, unlike what my picture's showing you, okay? So we have a force that's being applied on this column, coming down like this. And this is an 80, we're going to call it 80 kips. Okay, I think your book uses 80,000 pounds, but I'm going to call that 80 kips. And we are given that the area of 1 rebar is 1 inch squared. Okay, so the area of one of these guys is 1 inch. Okay, so that's 1 steel bar. And this guy is 10 inches by 10 inches. All right, so this is the steel right here. All right, we know E's are given, E for steel, and they give us, in this problem, they give us 30 times 10 to the 6th PSI. Okay, so if you go back and look at that table, 8.1, you'll notice it is 29 times 10 to the 6th. So remember, steel can vary from 28 to 30. So in this case, they're giving it to us. And for the concrete is given as 3 times 10 to the 6th PSI. So in this particular problem, they don't tell us the length of the column because the length of the column is really immaterial because we know that that's going to cancel out. Okay. So let's tackle the areas first. So we know that we have 4 bars. So the total area of the steel is going to be equal to 1 square inch times 4 bars. So the total area of that steel is 4 square inches, okay? So you're told that this is 1 square inch, so we got 4, that's where I'm getting my total. So the area of the concrete is going to be equal to 10 times 10 minus 4 square inches. Okay, so let's see what we come up with there. We got 10 times 10 gives me 100, minus 4 gives me 96 square inches. Okay, so that's important. Everybody understand that, right? We're just subtracting those areas out. No problem there?
Nope.
Okay, so if we look at the statics on this, based on what we just said before, in a y direction, we know that the force of the steel plus the force of the concrete minus 80 kilonewtons, or kips rather, has to be equal to 0 by equilibrium. So all that really essentially tells us is that the force of the steel plus the force in the concrete has to be equal to 80 kips. That's all we know. Okay. We also know, because these materials are acting parallel and they're in concert with each other, that the deformation of the concrete has to be equal to the deformation of the steel. So therefore, again, we know that deformation is PL over AE. So we have PL over AE for the steel must equal PL over AE for the concrete. And since we're assuming equal length, those guys cancel. So what that gives us here is force of the steel is equal to 1 over AE of the steel, which is equal to P of the, whoops, I got one of these things wrong here. Let me go back here. I got steel and steel on both sides. That's not right. I should have concrete here. Change that to concrete. Force of the concrete is going to be 1 over AE of the concrete, okay? So the material itself, area of the steel times the area of the concrete, 1 over that, and then this is going to be the same thing on this side. So to solve in terms of one or the other, if I solve in terms of steel, I'm going to multiply both sides by the 1 over AE. Essentially that cancels. What you get when you do that are just AE. What you wind up with then is this equation. AE, oops, not C. AE of the steel divided by AE of the concrete. Okay, so that's what we've kind of been expecting. So we can plug numbers in now, and we're already in square units. These problems are so much simpler when you're not dealing with metric, okay, like the last one. So we have the area of the steel. Now, make sure we get the right one with the right thing. I did this. Sometimes you get the wrong area with the wrong modulus. It's going to blow you out of the water here. So the E of the steel is 30 times 10 to the 6th. Does everybody agree with my constants? Area is 4 square inches. Steel is 30 times 10 to the 6th. And then for concrete, we have more concrete, so that's 96 times, but it's got a much smaller modulus of elasticity. And all of this is going to be times P sub C. So what that gives me is P sub C, whoops, PS is going to be equal to, when we do that math's a little bit easier to deal with. Let's see what we come up with. Anybody get a number? I got 0.4167 P sub C. Anybody getting that number?
Yeah.
Okay, we good? So this now can be plugged back into your statics relationship. So what we now have, if we look at this, we know that because steel is related to that, we have 0.4167 P sub C plus P sub C has to be equal to 80 kips. So again, don't forget you have a coefficient of 1 out here. So that gives you 80 divided by 1.4167. Okay, so 1.4167 check your numbers. I got 56.5 kips. And so therefore the force in the steel is 23.5. Is that what you guys are coming up with? Here's the one answer. Here's the other answer. That look right? You guys getting it?
Yeah.
Okay. Any questions?
We'll do. Are we able to do some of these problems on Thursday?
Yeah. Yeah, definitely. That's not going to be a problem at all. Not going to be a problem at all. You want to try another one? You guys think you got it? We try another one?
I'm maybe gonna try one on my own, but
Okay.
it doesn't matter.
That's fine. Like I said, we're gonna be working these things. I got some extra. I might give you guys some extra ones on the board too. Sometimes it's easier to do it on the board for you, I think.
Yeah.
Okay. So, well, with that, then basically that's it for my lecture today. I will go ahead and record or finish the recording. There are problems in the back of the book for you to do now. Okay. So they're listed on your syllabus. They're also listed on the on our page. Let me go back here. Let me see. See, so for week, let's see, we are in week 10. Huh. You guys should have had that. Should have been turned on. Were you guys able to get to this today? For some reason, I must have turned that off. I apologize. You should have had these notes here. But there's problems here. I want you to work 1, 2, 4, 6, 7, 10, and 13. Wow, I thought that was turned on. Yeah, let me turn that on for you now. Okay, so I'm going to stop the recording real quick.